Here's the fourth video of chapter 6, picking back up with orbital diagrams. So let's look at iron. Iron, we already saw the electron configuration on the last page of your notes. So we start filling in. Remember, S's only get one blank for one orbital, and S gets one blank again. The P's get 3 blanks. S gets 1, P gets 3, S gets 1 blank, and then the D's get 5 blanks, right? Because there's 5 of those orbitals at each level. And then you fill them up accordingly, but here's a really important rule. So iron has the configuration 3d6. Remember a little while ago we talked about degenerate orbitals. They're orbitals that are identical in size and shape, and therefore they're identical in energy. So these 3Ds will actually get filled up one at a time because electrons don't want to share an orbital unless they have to. So what we know is the atom chooses to put all of his electrons up or all of his electrons down first, and then come back and fill them in with a second electron. This is called Hund's rule. And so when you get to degenerate orbitals or repetitive orbitals, you have got to fill them in one at a time with all up arrows or all down arrows, whichever you prefer. So I did 1, 2, 3, 4, 5, and then I was forced to share that 6th one. And here for the noble gas, I could have put argon all the way up to the 3p6, and then I would have shown the rest of this, the 4s2 and the 3d6. So that's called Hund's rule. I'll show you one more. With the Nd, we also did Nd on the last page. And xenon, the noble gas configuration was xenon 6s2, 5d1, 4f3. So the way we would do that is 6s would get the 2 electrons, 6s2. 5d, I could have gone ahead and drawn 5d blanks. Only one of them gets an electron, but it's fine to have the others sitting there blank, no problem. But 1 electron in the 5d, and then the 4f's are important here. There are a total of 7 4f orbitals available. I could have drawn all 7, but I only had 3 electrons to place. So Hund's rule tells me place them one at a time, all in the same spin, up, 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 and I would not come back and fill those in until all 7 have 1 electron. So that's really important, is the Hund's rule. So paired versus unpaired electrons. We can count these once we have drawn our orbital diagrams. If we look at Nd right here as an example, paired electrons are just where an orbital has 2 electrons. So this atom has 2 paired electrons that I can see right here, and 4 unpaired electrons that I can see. 1, 2, 3, 4. You also can distinguish valence versus core electrons. So core electrons are inner electrons in an atom. They are not involved in chemical reactions. The valence electrons are the ones that get involved with chemical reactions. So these are the electrons that are found in the outermost energy level. So if we look here, magnesium, we know that his noble gas configuration is neon 3s2. So we look at this largest energy level here, 3, and we look how many electrons does he have in there? He has 2. So that gives him 2 valence electrons. For iron, if we have argon 4s2, 3d6, you only go to the very biggest energy level, which is 4. And he has 2 electrons there, so he also has 2 valence. The 3d6 don't count because they're at energy level 3. They're not at the outermost level. So valence electrons, if I show you one more, let me scroll up and show you one more. Something like neon here. If you look at neon, 1s2, 2s2, 2p6, the energy level that's the biggest is 2. And you want to look at all of those. So at n equals 2, you have a total of 8 valence electrons here, 2 and 6. So you count up any and all electrons that are found at that biggest energy level. Okay, we also can draw electron configurations for ions, which remember ions are charged atoms, so they have either gained extra electrons or lost some electrons. So all you do is simply calculate the number of electrons they have and then follow the normal rules. So O minus 2 Oxygen normally has 8 electrons, but he gained 2 more, so he has 10. That actually makes him isoelectronic with neon, so you really can write just plain neon because he has the same configuration as neon, but you also could write it out as 1s2, 2s2, 2p6, and it adds up to 10 electrons. Mg plus 2. Magnesium normally has 12 electrons, but he has lost 2. That's how he became plus 2. So he also has only 10 electrons. He's also going to look like neon, 1s2, 2s2, 2p6. I would not know that these were ions unless I were told. So if you see just normal neon, you assume he's neon. But we also want to understand that that could stand as the electron configuration for different ions that have gained and lost electrons. Transition metals, they lose electrons in a little bit different way than you would expect. So if you see iron and you wrote out his normal configuration, it would be argon, 4s2, 3d6. Well, how many valence electrons are there and who are they? Valence electrons are in the outermost shell, which is n equals 4. So these 2 electrons right here are in the outermost shell. They will get lost first because the 3d, those are kind of embedded. They're underneath those first 2 electrons. So for transition metals, if it's Fe plus 2, think about what that means. He needs to lose 2 electrons. He will lose the 4s2 first before he starts losing the 3d electrons. So Fe plus 2 would be argon, 3d6. Fe plus 3, he needs to lose 1 more electron. So he first lost the 4 s's, and now he goes and starts losing the 3ds. Ground state versus excited state. Ground state means that an atom is in its lowest energy state, its most stable state. Excited state means an atom has been given extra energy. The way you can tell a difference here is the ground state follows our rules. It fills up in the manner that you expect, whereas excited state is when some electron has jumped out to a higher level or a different orbital. You see how this one down here does not follow our traditional rules. 1 electron has been hopped up to a p orbital. So this would be the ground state. That's what we can predict. Excited state is when electrons have jumped up. The last thing here is to show you a couple of exceptions for special cases of transition metals. This occurs for transition metals that fall either at D4 or D9. What I mean by that is D4 comes right here at D1, 2, 3, and 4. Chromium and his group, those are D4s. And copper's group, here, they make D9s, okay? What we know that these atoms choose to do is they actually choose to rearrange their electrons so that they have a half or a full D shell. Let me show you what I mean. You would predict copper to be argon 4s2 3d9. You can go count that and look at it yourself. But in reality, what copper does is he takes one of these 4s orbital electrons and bumps it to the 3d. What that does is brings it down to 4s1 and brings it up to 3d10. We think that's because having this full d orbital and set of orbitals is more stable for the atom. Same thing with silver. He's going to look really similar. 5s2 3d9. Because he's 3d9, he will just pop 1 electron over, bring 5s down to 1, and bring the 3, oh, that should be a 4d9, I'm sorry. 4d9 will change to 4d10. So what he's done is taken one of his s's electrons and hopped it over to the d to make it full. And then very similarly over here with the d4s, they're going to hop over to d5s because the d5 gives it a half shell, half filled shell. So if you see a d4, what we know is that one of the s electrons hops over and brings it up to d5. Okay, and I'll fix that 1 or 2 little typos here in your notes. So we know that D9s turn to D10s and D4s turn to D5. So the predicted is not a correct picture of the actual.